Next class, I guess, at the at midnight of the next day is the homework 5 is due. If you haven't used your extension, you can use the extension. Any questions about homework 5? While people are thinking about that, it should be the dynamic programming problems and the some NP-completeness problems. I think the NP-completeness problems will be a lot clearer after today. Any questions about that? Later on, after that, we will start to, next class, I'll talk about the final, and, and if there's any questions people want to save up for me tomorrow, there's a chance we'll have, next class, there's a chance we'll have time for that. Any questions? Yes? Is there going to be a practice final? And the answer is no. Okay, this is a live class, right? So you guys are going to be taking your final in here. You guys have a lot of practice taking the final because you have a lot of practice taking midterms. And the final will be just like the midterms. It is going to be a certain number of written problems. You had 3 on the midterms. I will expect you'll have 5 on the final. Okay, again, you have, oh my God, that's impossible. How much more time do you have on a midterm than a final? Okay, the multiple is more than the ratio of 5 to 3. So the answer is you will have more time, right? The number of multiple guess questions will go from will go up. Exactly how far it'll go up, I'll know. But again, expect something very similar to it. The only difference that is I will promise you one of the written problems will be about NP-completeness. That's the only promise that I will make to you. Okay, otherwise it's scattered around. Any questions? Okay, so I'd like to now talk about NP-completeness. And again, I promised you that every class I was going to talk about the exact same slide. And this is the big idea about NP-completeness. It has to do with an algorithm for solving the Bandersnatch problem. What is the Bandersnatch problem? It is some kind of problem. Actually, it is some kind of decision problem. We like decision problems, where the answer to is going to be a yes or no. Okay? So Bandersnatch is going to be some decision problem, like satisfiability, like traveling salesman. Is there a traveling salesman tour of length greater than 106? Okay? Is there it's a yes-no problem. And this Bandersnatch algorithm works in the following way. It translates the input of Bandersnatch. Perhaps it was a graph, perhaps it was a set of logic clauses, perhaps it was points in the plane, perhaps it was whatever it was. It's G. And it translates it into a form Y, where Y is an input to something called the Bobilli problem. And it calls Bobilli of Y and returns that as the answer to Bandersnatch to G. And this algorithm is 100% correct if this conversion program has the property that Bandersnatch of G is always equal to Bobilli of Y. If we can do this kind of translation, then returning Bobilli of Y as the answer to Bandersnatch of G is a perfectly correct thing to do if the answers are the same. And if Bandersnatch is a yes-no problem, Bobilli has to be a yes-no problem. And whenever Bobilli of Y is yes, okay, Bandersnatch of G is yes. Suppose we have an algorithm like this, okay? You write an algorithm like that. What does this algorithm mean? It can have 2 possible applications. Assuming the translation here is fast. If the translation here runs in something like n squared, n cubed time, that's what I mean by fast. Okay? If the translation is fast, what does this mean? If you could solve mobility of Y fast, you would solve Bandersnatch of G fast. So if there is a fast translation and a fast algorithm for mobility, this gives you a fast algorithm for Bandersnatch. Okay? That could be a useful thing. If, on the other hand, you have a promise, a reason, a proof, an argument that there does not exist, okay, a fast Bandersnatch. No fast Bandersnatch. Okay, there is a lower bound argument. There is some kind of statement that you know why Bandersnatch can't be solved quickly. This algorithm proves that if you could solve mobility quickly, you would solve Bandersnatch quickly. This would give you a fast algorithm for Bandersnatch. If there is no fast way of solving Bandersnatch, and this algorithm using mobility would be fast if mobility was fast. Therefore, mobility can't be fast. And mobility is as hard a problem as Bandersnatch is. That is the main way we're going to use it in here. This is the reduction. This is the reasoning that we're doing. Any questions about that reasoning? Okay. Any questions? Now, what Bandersnatches do we have in our world here? Okay, so far we've talked in class a little bit about that. What is a good example of a Bandersnatch? Candidate for Bandersnatch here. Yeah? The what? Okay, you're saying traveling salesperson. Okay, I'm going to write this down, traveling salesperson. Now, I didn't really prove to you. I've been mumbling that the traveling salesman problem is hard. I didn't really show it to you yet, right? I didn't really give you any way other than me, a lot of loose talk running around, okay? Does happen to be hard, but that's not it. Which ones do we know about? We know about satisfiability, not sustainability. Sustainability is something you learn about in an environmental class, right? Satisfiability. Which was that it took a set of logic clauses on a set of variables, and it decided whether or not there was a way to make it true. Is there any other candidate Bandersnatch that we have seen here, that we've worked through? Okay, yeah, in the back.
Vertex cover?
What? Vertex cover, I haven't done that yet, but we're going to do that very soon, okay? So for now, if we're developing the whole theory from the beginning, I haven't yet dealt with vertex cover. What's the other one? Somebody. Yeah? Three-set. What was three-set? Three-set was also a logic problem. It took a set of logical clauses and variables, but where every logical clause had exactly three things in it. Okay? That was what was important about three-set. Both of these are hard problems, equally hard. Okay? Which one of these makes for a better, more pleasant Bandersnatch? Let's think about this. This is a philosophical question here. Which one of them makes for a nicer looking Bandersnatch? Okay, does anyone have an opinion? Yeah? Three-set. Why do you think three-set makes a better Bandersnatch? Because it's what?
Simpler to work with.
Simpler to work with in what is the job of a Bandersnatch? The job of a Bandersnatch is to be translated into a mobility. Does everybody agree? That's why we have a Bandersnatch. Now, in full satisfiability, you can have very long clauses, you can have short clauses, you could have all clauses be length 3. In three-set, your clauses are exactly length 3. Does everybody see that the universe of satisfiability problems is bigger than the universe of three-set problems? It's a more restricted thing, right? If I said, what is it easier to work with? Let's say you wanted to turn a house into a car. Would it be easier to translate all houses into cars or greenhouses into cars? It's certainly not going to be harder to translate greenhouses into cars than the whole set of possible houses, because, greenhouses are houses, okay? So that's why we're going to care about three-set. It's a Bandersnatch. It's every bit as hard as satisfiability, but because it is simpler, okay, maybe it will be easier to do transformations from it. Any questions? That's the philosophy here. Any questions about the big picture? Now, I can imagine you're not that excited about three-set, frankly. You never saw three-set before I started talking into it about how hard it was. Okay? But let's look at a problem now that is a problem that you've heard about that seems like it seems like a problem someone might pay you to do something with someday. Okay? And that is the vertex cover problem. Let me just try this thing here. What is the vertex cover problem? We actually had a homework assignment about that. Vertex cover problem is on graphs. What is the problem? It is actually the vertex cover decision problem, because we need it to be yes or no. Okay, we're saying that a vertex cover is a set of vertices such that every edge kisses, okay, one of the vertices in the set. Here I've got a graph with, it looks like 8 vertices in it, right? Does everybody agree that if I take these circled vertices, every edge kisses at least one, that one kisses 2 of them, kisses at least one of the circled vertices. Does everybody see that that's true? What if I take a different subset? Let's take this, 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 and this. That's 4 vertices. Does every edge kiss at least one of these? Which edge is unkissed? Actually, this one is unkissed, this one is unkissed, and this one is unkissed, right? So the circled vertices make a cover, okay? They're a set of vertices that cover all the edges in the graph, okay? Any questions? Does this sound like any other problem that you guys had in this class? Was there another problem that you guys have dealt with here that smelled a little like vertex cover? What was it? Minimum set cover, right? Is minimum set cover, is vertex cover a special case of the minimum set cover? Actually, it is, okay? Because notice that you want to pick a set of vertices. If you think that each vertex comes with the set of edges that it covers, okay, then in fact you want a vertex cover, okay, can be thought of as a set cover problem for a specific type of set cover problem. It's not clear that every set cover problem is a vertex cover problem. But it is clear that vertex covers are a type of set cover, okay? And if I prove that vertex cover is hard, I'm going to be able to use that to prove that set cover is hard, okay? General set cover is hard. And that's why I knew you weren't going to come up with a fast algorithm for your, in your backtracking problem, okay? Any questions? So vertex cover is It's a decision problem. I'm given a graph, and I'm given a bound, and I'm asking, is there a subset of, at most, k vertices, such that every edge has at least one vertex in the cover? What would be an example of a set cover problem that is easy? If I give you a graph, is it hard to find a set cover of a graph? Okay, how do you find a set cover of a graph? Yeah? Take all the vertices, right? Finding it, so that's not a big accomplishment. Finding a small set cover is where it's going to be difficult, right? And the decision problem says, is there a subset with at most k vertices? Okay, such that every edge is covered. Any questions about what vertex cover is? The problem. Now, if I want to prove it's hard, what should I do? What is my strategy going to have to be? I'm going to be going back to my Bandersnatch. Let me go back to Bandersnatch and mobility again. I know that looks a little out of control. If I want to prove that set cover is hard, if vertex cover is hard, what should be my Bandersnatch and what should be my mobility? Okay? What is Bandersnatch going to be in trying to prove set cover is hard? Vertex cover is hard. Yeah? I should say 3 set. And what is my mobility? Vertex cover decision problem, which took as input what? A graph and a bound k. And 3 set took a bunch of logic clauses and variables. In order for me to do this, I've got to find a way to translate any 3 set into a vertex cover problem, such that that graph is going to have a small cover if and only if the original set problem is satisfiable. Okay? How can I do this translation between logic clauses and a graph? Let me show you a way to do it, okay? Because it's kind of a clever little thing. I'm going to translate my 3 set problem, which has n variables, which are n Boolean variables that can be true or false, and it had m clauses, each of which had 3 literals in it. And I'm going to show you how to take that logic instance and create a graph with 2n plus 3c vertices. Okay? And I'm going to do this translation in pieces, okay, so that I know what the size of the vertex cover of this graph is. Okay? First part of my piece is I'm going to take the n logic variables and create a graph consisting of 2n vertices, which is disconnected. It's connected into n components. I'm going to label my vertices V1 and not V1, V2 and not V2, V3 and not V3, Vn, not Vn. And I'm going to connect each vertex to an edge, by an edge to its complement. Now, so far, I have a graph with 2n vertices and n edges. Does everybody see that? See what my graph is? It's just n isolated edges here. Okay? What is the size of the optimal vertex cover of this graph? What is the smallest possible vertex cover you can build on this graph so far? Yeah? N. Why is it n? In order to cover this edge, I've got to do what? I've got to either pick this or I've got to pick that. Does everybody see that? I could pick both of them, but that's not necessary, right? Picking either of them will cover the edge, and because these are disjoint edges, there is no possible way to cover those edges in less than one edge per pair, one vertex per pair. Does everybody agree with that? The minimum vertex cover of this thing is going to be n. N vertices is the minimum vertex cover here. And how many different minimum vertex covers are there here? Okay, let's see if we understand it. How many different vertex covers are there that are minimal? Yeah? 2 to the n. Why is it 2 to the n? I've got 2 choices for every one of these things, right? I could pick the left vertex or the right vertex of each pair. Okay? I have 2 to the n different minimum vertex covers of this graph so far. Okay? Any questions? What else are there 2 to the n different things of? Is 2 to the n a thing we know about? What else in this world do we know about? If we have a 3-set instance with n variables, how many possible ways are there to assign true and false to those variables? How many? If I give you a satisfiability instance on n, where there's n logical variables on it, not all of them will make it true, but how many different ways can you flip those variables to true or false? How many ways? 2 to the n. Do you see what I'm doing? I'm doing my translation. I am building a graph where there is something that is doing the same thing as my logic. That's the idea here that's going on. Does everybody see that? Okay. Any questions about that? That's where my idea is coming from. Okay, but let me continue to build my graph. That's not the end of my translation. I also want to use add another 3 times the number of clauses vertices. How am I going to do that? Well, what if I, for every clause, create a triangle? And it looks like I didn't do a good job making it visible up there. Boom. That's probably better. Okay? I am going to take a clause like V1, not V3, not V4, and for every such clause, I'm going to make a triangle of vertices from it. Okay? Look at this here thing. Do you see how that is 3 new vertices that are connected in a triangle? Okay? And the labels of these vertices are exactly the labels of my literals. Okay? If I give you a triangle like this, let's say I do it like this. Let's build it again. Uh-oh, trouble. V03, V1, V4, bang. What is the minimum vertex cover of this 3-vertex graph? Okay. How many vertices do I need to cover this triangle of vertices? 2. Which 2? Any 2. Does everybody agree with that? If I pick this vertex and this vertex, I get that edge twice, this edge and this edge. Do you see that if I have a triangle of vertices, I need any 2 of those vertices will cover all 3 edges in the triangle, right? Is there a way that I can cover the triangle in fewer than 2 vertices. There are 3 edges. Is there any way I can cover all the edges with fewer vertices? What do you mean? If I got 1, I got this edge, I got that edge, but what's the problem? I do not have that edge, right? So I'm going to claim that if I just build a graph which has a total of 2n vertices and 3c vertices, okay, 3 times the number of clauses. Forget about these connections between them. Let's just say that I have these n isolated edges and these c isolated, triangles. What is the minimum vertex cover for that graph? The graph has c plus n different connected components, right? What is the size of the smallest possible vertex cover for that? Yeah? N plus 2c. Does everybody see it? I've got to pick 2 out of the 3 for this triangle, 2 out of the 3 for this triangle, 1 of the 2 for that edge, 1 of the 2 for that edge, 1 of the 2 for that edge. The minimum vertex cover has got to be equal to 2n plus, no, take that back, n plus 2c. Okay? Any questions about that? Now, suppose I add extra edges to the graph. Is the vertex cover going to get bigger or smaller? Let's say I give you a graph that now looks something like this. Right? This is what it looks like now. If I add edges to this thing, is the size of the vertex cover going to get smaller or larger? Okay? I want you to think about this. If I add edges to the graph, can the vertex cover size get smaller? Answer is no. Why? It's more work to do. Does everybody kind of see that? If I, if I don't add edges, if I add an edge, let's say I have a vertex cover for this now. Okay, let's say kabunk, 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 bunk, 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 bunk. There's a minimum vertex cover. If I add an edge like this, the vertex cover didn't change, right? If I add an edge like this, the vertex cover might change, right? It might require more work to do now that I add an extra edge. Or maybe not. What if I instead take this vertex out of the cover and add this one instead? Do you see now I've added another edge and the cover didn't go up? Okay. Those red things are still a vertex cover even though I add more edges, right? So if I add edges between my, what I'm going to call vertex gadgets and my clause gadgets, maybe the minimum vertex cover isn't going to go up, but maybe it will. Okay? Now let me tell you how I'm going to add these extra edges. I am going to add an edge between every one of my clause gadgets. I had 3 vertices in it. Each vertex represented a literal in a clause. I'm going to connect each edge of each corner of my triangle to the variable gadget with the same name. Do you see that? I have connected this thing to the variable gadget with the same name. Okay? Adding these edges, and I'm going to do that with the second one. This one goes to V2. This one goes to not V1. This one goes to not V4. Adding these edges can only make it harder to have a small vertex cover. Right? My claim is going to be that after I have done this translation, this graph is going to have a vertex cover of exactly this size if and only if the original graph logic expression was satisfiable. Okay? You see how I translated, you should see how I translated the logic thing into a graph. Okay? The interesting thing, and that this is a mechanical thing. If I ask you to do this for homework, here's a logic expression, make this graph, this is mechanical. You can do this. You could write a program to do it. Okay? But what's interesting about it? My claim is that if this expression was satisfiable, there is still going to be a cover of this size. Why is that? What does it mean for something to be satisfiable? If I have a satisfying truth assignment, let's say I do this, 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 and this. That happens to be a satisfying truth assignment. Why do I know it? Because there is an edge from one of these vertices to every one of my clause gadgets. See that? V1, V2, V3, V4, all being true, is a satisfying assignment. Why is that? Because if I make, again, what were my clauses? My clauses were V1, not V3, not V4, V2, not V1, V4, not V4. Does everybody agree that V1 being true and V2 being true is a satisfying truth assignment? I've got a true in every clause. But what does that mean? That means that when if I pick the vertices on top corresponding to that satisfying truth assignment, what do I know? I have covered at least one of the edges to every triangle. Right? How do I now cover the rest of the edges using two vertices per clause? Does everybody see that if I pick this and this, and this and this, all the edges in the vertex cover problem are covered? Okay? Why is it? I need to have two vertices per triangle. I have to do it. What does each triangle look like? The triangle now looks like three vertices plus there's an edge on every vertex going back that still has to be done. If at least one of these edges is taken care of by how we did this, I could cover the rest of it by picking the other two. But, okay, if you give me something that's not a satisfying truth assignment, what's not a satisfying truth assignment? Let me see if I could find one. This. Let's say I did this. Does everybody see that that's four things? It covers all the clause variable vertices. But is it satisfy? Well, this V1 takes care of that edge, right? So I can finish the job there, and in two vertices, I have covered all those other edges. But now do you see that I'm stuck? I got to cover this edge, and this edge, and I got no help from my truth assignment. There is no way I can cover the three edges of my triangle and those three connecting green edges by just using two vertices. Does everybody kind of see that? If you have a satisfying truth assignment that has the property that every clause will have at least one of its edges covered, okay? And if there is no such satisfying truth assignment, then the minimum vertex cover is going to be greater than n plus 2c. Okay, you're going to have to use more vertices to cover the edges. So if you understood that translation, what I just argued is this graph that we build will have a vertex cover of this size if and only if the original problem was satisfiable. Okay? Any questions about this reasoning so far? How many people sort of see what I'm doing here, where I'm coming from and why? Okay? Any questions about this? Any questions about this construction? So what am I now doing? I have now shown that I have shown a translation from a three-set problem to a graph such that this graph, to a graph G, such that this graph has a vertex cover of this size if and only if the original thing was satisfiable. Okay? And if I could come up with a fast vertex cover solver, this would give me a fast three-set solver, wouldn't it? If I had a way to whoosh, find a vertex cover quickly in a graph. If I did it on this graph, I'd say find me a vertex cover, the minimum vertex cover. And it came back and said ka-chunk, 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 ka-chunk. Okay? It would say, yes, you do have a vertex cover here. Yes, it is of size n plus 2c. And once you give me that cover, I can read off what was a truth assignment to your formula. The great thing here is that if I can find a cover of this size, your three-set problem was satisfiable. If I could solve vertex cover quickly, I could solve three-set quickly. But can I solve three-set quickly? I cannot solve three-set quickly. So what does this prove to me? This proves I cannot solve vertex cover quickly. Any questions about that? Okay. Now you may say, how did someone come up with this translation? That looks really weird. And the answer was the first guy to do it was smart. Okay? But once you see some of these, it turns out once you've worked with these things, there's sort of a logic to it. I tried to explain the logic to these things. Okay? And normal human beings can find things like this, okay, with enough practice. Any questions? Okay? Any questions about what that means? Okay. So I'm claiming that I have just proven that vertex cover does not have a fast algorithm unless 3-SAT does. And since 3-SAT does not have a fast algorithm unless SAT does, and since SAT does not have a fast algorithm, therefore vertex cover is as hard as satisfiability, and vertex cover is hard. Any questions? Okay. Once you've done that, now we have another Bobilli, right? Bobilli is a good vertex cover. Once we have, once we have another, the more problems we have proven hard, any one of our hard problems can serve as a Bobilli, as a Bandersnatch, excuse me. Okay? And the more and more hard problems we have, the more and more the easier and easier it will be to prove other problems hard. Let's take a look at a different problem on graphs. This is a problem we talked about at the very beginning of class also, just like when we were talking about TV. We talked about the movie star scheduling problem. What was the problem? The maximum independent set problem on a graph asks us to find a large independent set, a large set of vertices such that there is no pair of the vertices have an edge between them. Okay? I claim, if we take a look at this particular graph, these two vertices form an independent set, meaning that there is no edge between any pair of them. Right? Can we make it bigger? Is there an independent set of size 3 in this graph? Yeah, which 3?
You have the one in the middle of the left. The one, that one.
Saying these 3. Those 3 form an independent set. Does everybody kind of agree? So in fact, that's interesting here. Why do I think that this is so? This has an independent set of size 3. It certainly looks right to me. Okay? Remind me of that, somebody, so I can remember to change the slide. Okay? Does everybody see that that's an independent set? An independent set of vertices is a set of vertices such that there is no edge between them. Okay? What would the independent set be, an independent set be in Facebook or Instagram? You guys have a social network. If I have a set of people and I say they form an independent set on Instagram, what does that mean? Yeah? No two of them are friends with each other. They're all mutual strangers. So maximum independent set is trying to tell me what is the, maximum independent set is trying to tell me what is the largest set of mutual strangers you can find in a network. Does everybody kind of get that idea? Okay. And this is also kind of a useful thing to find sometimes. If, let's say, this was a scheduling problem, and 2 classes that you couldn't take at the same time had an edge between them. Let's say that these 2 courses, there was a conflict in doing it. You couldn't take both of them. Maybe they met at the same time. Maybe they covered the same material. Maybe something like this. Okay? The maximum independent set would be, what's the largest number of credits I could get in a semester? Okay? meaning a set of courses that wouldn't mutually interfere with each other. Any questions about that? Okay. Does everybody understand the maximum independent set problem? Okay. If we wanted to prove the maximum independent set problem is hard. Is maximum independent set going to be Bandersnatch or Bobilli? Okay, if I want to prove that maximum independent set is hard, right now you don't know anything about it, right? You just know it's about creating a bunch of mutual strangers on Instagram. If we want to prove that this is hard, is maximum independent set Bandersnatch or Bobilli? It is Bobilli. Okay? And what should Bandersnatch be? Bandersnatch should be a hard problem, okay, that we can choose from, right? What hard problems do we know about so far? We know about set. We know about 3 set. We know about vertex cover. If you listened carefully to what I said, we knew about set cover, I guess, is also hard. Set cover, a special case of set cover, is vertex cover. If we had a fast set cover program, you could use it to solve vertex cover. Okay? Which one of these problems, if they're going to be my candidate Bandersnatches, which one of these smells most like maximum independent set? Do any of these problems smell more like maximum independent set to you than another? Does anyone have a sense of smell about this? Sense of taste. Maybe it's a sense of taste more than a sense of smell. Which one of these looks most to you like which one? You think vertex cover looks more like that. Why does vertex cover look more like it? Vertex cover is what? You're saying it's the opposite, and that's now a deeper thinking than I'm trying for. I think it looks better because this is a graph problem. Does everybody agree that vertex cover is a graph problem? This is a logic problem, set problem. Maximum independent set is a graph problem. So I think I see some level in which they look better, similar. What else? What other way do they think look similar? Minimum vertex cover wants me to find what? I guess it wants me to find a small set of vertices such that all the edges are covered, right? Maximum independent set, I want to find a large set of vertices such that there's no edges on there, right? I guess that doesn't immediately seem like an obvious thing. Although, is there a connection between vertex cover and an independent set? Is there a way of looking at these that they are kind of, sort of the same thing? Okay. What happens if I take everything that is not in my vertex cover? Let me just take a look at this thing. You told me that my maximum independent set here is this, this, and this. Does everybody agree? What do I know about the remaining vertices? How many edges are there that both of their endpoints are on my independent set. Okay, every edge has how many endpoints? How many endpoints does that edge have? Here's an edge. How many endpoints does that edge have? 2. Okay? Is there any edge that has both of its endpoints in my maximum independent set? Is there an edge like this? No. Can there be an edge like that? No. What is an independent set going to be? An independent set, remember, is a set of vertices with no edges defined between them. Right? An independent set is a set of mutual strangers. Does everybody kind of get that? See, I'm getting people staring at me. Okay, I'm not getting the nodding that I like to see. I'm getting the nodding off I don't like to see. Okay? What is it that I say? There is a connection, an interesting connection between vertex cover and independent set. What is it? If the black vertices represent the black vertices were everything that was not in the independent set. This was my independent set, right? What do I know about my black vertices? The black vertices are the vertices that were not in my independent set. What do I know about those vertices? Yeah? They have to be a vertex cover. Why? If no edge goes between two edges in my maximum independent set, if there is no edge like that, every edge is either between two vertices that are outside the independent set, or they are edges with one vertex outside the independent set. That means that the set of vertices that are not in an independent set are a cover. Let's take a look at this thing. Are these two vertices an independent set? Are those two vertices an independent set? Yes, it's not the smallest one. Actually, let's make it a little differently. Let's take these two. Are these two vertices an independent set? Are all the other vertices, the n minus, in this case, 2 vertices, do they represent a vertex cover? Well, if I pick this vertex, the black vertices now, boom, 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 those have to be a vertex cover. Why? Because every edge is going to kiss one of these. If we have a graph of the form where there is an independent set here with nothing in it, no mutual edges, and all the edges in the graph either are from this or go to other vertices, if these 4 vertices are an independent set, everything else, the rest of the vertices, all the vertices that are not red, are going to be a vertex cover. Do people see that this is true? This is one you should be able to see is true. So I'm going to say this again in the hopes that people see that it's true. Because this is the level of reasoning that I think you can do. Making that logic to graph transformation, maybe that's too complicated. But this is a very simple transformation, right? If you have an independent set, all the vertices except that independent set must form a cover. Because every edge is either going to be between two vertices that are not in my independent set, or they are going to go from something in my independent set to something outside. There cannot be an edge between two vertices in my independent set, because then it wouldn't be an independent set. Then these two vertices, they're not mutual strangers then. Does everybody see that now they're not mutual strangers anymore? If I delete this edge, they are mutual strangers. Any questions? So what does that mean? Let's go through this logic a little slower. Okay, I'll just come back down here. Okay. What does it say? There is a connection. If you give me a, the claim here is that if you give me a vertex cover and you delete it, you get an independent set. Okay? If you give me an independent set and you delete it, you get a vertex cover. Okay? So finding the smallest vertex cover is the same thing as finding the biggest independent set. Okay? Let's take a look at this thing. Are the red set of vertices, let's look at this one here. In this one, are the blue vertices an independent set or a cover? Let's look at this. I've got blue vertices and red vertices, right? Actually, in this graph, it's kind of interesting. It may be that they're both. Now, notice that the blue vertices, are they an independent set or are they a cover? Okay, what do we know? Are they an independent set or a cover? Yeah, what is it? Independent set. They're a set of four mutual strangers, okay, passing in the night, right? What are the red vertices? The red vertices, my claim are a cover, right? Why is that? If no edges are completely defined, but where both endpoints are blue, every edge is either going to have one red and one blue thing, or it's going to have two red things. It can't have two blue things, because then my blue thing wasn't an independent set. Now, is it hard to find an independent set of a graph? It's easy. Boom. There's an independent set, right? Is it hard to find a vertex cover of a graph? No. Boom, 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 boom. I got a cover. But my claim is that the biggest independent set, the leftovers will be the smallest cover, and the smallest cover, the leftovers will be the biggest independent set. So what does that mean? If I gave you a fast algorithm to solve vertex cover, suppose I really had a fast algorithm for vertex cover to find the smallest vertex cover, how would you find the largest independent set? Yeah? Find the smallest independent vertex cover and delete them. And what's left would be the largest independent set in the graph. Let's write that out as an algorithm, because I like to write these algorithms as a reduction. Does everybody see that I could solve the vertex cover decision problem? It took a graph G and a bound K. Is there a vertex cover of K or smaller? Does everybody see that the following algorithm would work to solve it? If I said, let me make a new graph G prime that's going to be the same as G, and I'm going to say, let's make a new value K prime that is n minus K. N is the number of vertices in that graph. And I call maximum independent set on G prime, K prime. Does everybody see that actually, if there is a maximum independent set in this graph of size this, that meant that there is a vertex cover in this graph of this size. Okay? This is my Bandersnatch algorithm, right? Bandersnatch is being played by vertex cover. Mobility is being played by maximum independent set. This is how I am proving that maximum independent set is as hard as vertex cover. Any questions about that? This is the kind of thing that I expect you to be able to do on an exam. Do you see my Bandersnatch mobility? You see how I wrote this here thing? Okay. And what is the transformation? Basically, if I can find a maximum independent set on what turns out to be the original graph of size n minus k, then that means there had to be a vertex cover of size k in the original graph, namely the vertices that weren't in the independent set. Any questions about that? Okay. And suddenly, boom, we have another interesting problem we know how to do that we have just proven to be hard. Any questions about that? Let's keep going. There is a problem on, which is commonly done thought of in social networks and in other things, called maximum clique. A clique is a complete subgraph. Do you see that those four vertices are connected? Every pair of them is connected to each other? The maximum clique in a graph is the largest set of vertices such that every pair of the vertices in it are connected. Okay? Any questions about that? What is the maximum, what is a clique in Facebook, Instagram? What is a clique in a social network? What would it be? Yeah? Everybody's connected to each other. Now, when I was in high school, people used to talk about cliques. Did people talk about cliques in your high school? Did anybody have a high school with cliques in them? Somebody with a hand who had a high school. What was a clique in high school?
The Asian kids.
Saying the Asian kids. Why did the Asian kids make a clique? It meant because every one of them knew each other. Is that right? Did they hang around with each other? Were they a complete subgraph in the social network?
Almost.
The answer is yes. For the purposes of this, the answer is yes. Okay? The notion of what is a clique in a graph? A clique in a graph is a group of people who everybody in it is friends. Right? And that is the problem. The maximum clique said, if you're Mark Zuckerberg, what is the largest, he might wonder, what is the largest group of people who are mutually, all pairs of them, friends? You could imagine Mark Zuckerberg running a commercial on Facebook. Says, hey, look at this, I've got these 173 people, and every one of them is friends on Facebook. Okay? Could Mark Zuckerberg do this? Well, unless he had a fast algorithm to find the largest clique, he couldn't. Is finding the largest clique in a graph going to be hard? You know what the problem I'm now asking? Find me a subset of vertices such that every pair of them is connected. Is that going to be a hard problem? If we want to prove it's hard, is clique going to be Bandersnatch or Bobilli? Bobilli. So I want an algorithm now where I'm going to be calling clique. What are the arguments to the clique decision problem? Looks like I've got a graph G prime, I'm going to call it, and a size J. What? Any questions here? Okay. Where's my Bandersnatch? What Bandersnatch problem should I use here? What choices of Bandersnatch do I have if I want to prove clique is hard? I could use satisfiability. I could use 3-set. I could use vertex cover. I could use independent set. I could use set cover. Which one of these smells most like clique? Do any of these problems smell like clique to you? What is a clique? A clique is a big set of people where everybody is friends. Is there any problem that smells a little like that? Yeah? Independent set is give me a big set of people where no one is friends. Right? You want to use independent set for Bandersnatch? Let's come back here again. Maximum independent set took as input what? It took as input a graph G and asked, are there k vertices such that, that none of them have friends between them? Is there a way we could use clique as a subroutine to solve maximum independent set? Okay. We agree. I'll write the part of the algorithm. G prime is equal to something, and J is equal to something. Okay. How would we use a clique solver to find a large independent set in a graph? Yeah?
We could run it first and then find, because the vertices that aren't in the maximum clique are definitely an independent set. So we can run it first and find an independent set, and then maybe remove a vertex from it.
Okay, so you're right now giving me an algorithm and not giving me a translation. Do you agree that you're trying to say, you're saying, yeah, maybe if you give me one of these vertex sets, I can do this, I can do that, I can do all kinds of things. You're not giving me a translation, yeah?
Could you run clique on the inverse of the input graph?
You're saying the inverse. What's the inverse?
Where there are edges between vertices that are not connected in the original.
Okay, what you're calling the inverse, I call the complement of a graph. Has anybody ever heard about a complement of a graph? A complement of a graph is replacing the edges. Here I have a graph. What's the complement of that graph going to be? It's that. Does everybody see that? So what are we going to do? First, you want to complement the graph. You say, nice graph, right? Okay? What if we say that this is going to be the complement of G? Now, what should J be? See what we're doing? We want to use a clique solver. You think that if I ran a clique solver on the complement of the graph, why did you want to complement the graph?
Because all the connected components in that output will represent vertices in the original graph that are not connected.
Okay, let me use my language. You were saying that if you have a clique, if you complement it, what do you get when you complement the clique? An independent set. And what happens when you complement an independent set? What do you get? A clique. So if I want to know how to find a maximum independent set of size k in a graph, what size clique should I look for in the complement? This is one that you think about for a minute, but I want you to get this one. Okay? If I want to find a clique of size k vertices in the graph, how big a clique should I look for in its complement? Okay. Suppose this is bad. Suppose I want to find an independent set of size 4 in the original graph G. If I complement it, what's going to happen to those 4 vertices? What's the complement going to look like? Bung, 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 bung. Does everybody see that? My claim is looking for a complement, an independent set of size 4 in the graph is the same as looking for a clique of size what in the complement graph? Yes? 4. So J should be equal to what? K. Ding, ding, ding. This is the reduction. Okay? Do you see how this is a Bandersnatch-Bobilli thing that I'm doing? Right? I am showing that if you knew how to find a clique of arbitrary size in an arbitrary graph, asking for a clique of k vertices in the complement of a graph that you want to find the independent set of. If you show me a clique of size k here, that meant that there was an independent set of size k in the original graph. Does everybody see that? So, we have proven that maximum independent set is hard. There is no fast algorithm for maximum independent set unless there is a fast algorithm for vertex cover, which there is no fast algorithm for unless there is a fast algorithm for 3 set, which there is no fast algorithm for unless there is a fast algorithm for set, but there is no fast algorithm for set. So there is no fast algorithm for maximum independent set. This would be a fast algorithm for maximum independent set if you could solve clique quickly. Does everybody see this? It's not hard to find the complement. Okay? If you could solve clique quickly, you would solve maximum independent set quickly. Okay? And this is the reduction. Any questions about this? This is the kind of thing I want you to be able to do. Okay? Any questions? And let me now go to the daily problem today, which I didn't go to, and let's see if you can do it. What was the daily problem? The daily problem said, show that the dense subgraph problem is hard. What is the dense subgraph problem? I give you a graph G, and I give you a vertex k, integers k and y, and ask, does this graph G have a subset of k vertices such that those k vertices have at least y edges between them? This is the densest subgraph problem. Okay, any questions about what the problem is? How would we reason that there is no fast algorithm for the densest subgraph problem? Is densest subgraph going to be Bobilly or Bandersnatch? Think about it. If we want to prove that densest subgraph is hard, is it Bobilly or Bandersnatch? Couldn't hear that. What is it? Okay. Uh-oh, trouble. Let's just make it like that. Those are the names of my variables. G prime, K prime, Y prime. What is my Bandersnatch? What hard problem that we now know of smells most to you like densest subgraph? Which one? Clique. Why does clique smell like densest subgraph for you? You're telling me that the clique is a platonically dense subgraph. That's the opposite of complimenting you, right? I'm saying you're as dense as possible, right? So what do you want to do? Clique. What were the arguments to clique? Let's say G and K. What would be my reduction here? If I want to turn it so that if I had a densest subgraph solver, how would I use my densest subgraph solver to solve clique? Yes?
Y prime is k times k minus 1 over 2.
You're going to say y prime is k times k plus 1 over 2. Where did that come from? Yeah?
Number of edges in the complete graph.
Does everybody see that in this case, k equals 5? How many edges are there going to be between a clique on 5 vertices? There's going to be 5, choose 2. No, that's not right. 5, choose 2, which is exactly what that is. What is k prime going to be? Finish my reduction here. What is G prime and what is K prime?
G prime will just be
G prime is just going to be what? G.
and k prime is just k.
Does everybody see that's what we want? Asking, is there a subgraph so dense it contains k vertices and k choose 2 edges? If you ask a graph, do you contain a subgraph with k vertices and k choose 2 edges? If they say yes, that means you found the clique. And if you say no, that means you did not find the clique of size k. Does everybody see that? This algorithm uses densest subgraph to find clique. Clique is as hard as anything else. Okay? If you could use this does show that you could use densest subgraph to find clique, but clique is hard.